Alright, so hello everybody. Today we're gonna keep working on our dynamics recitation class, and what we are gonna be doing today, we're gonna be calculating the mass moment of inertia for this first problem. So the first problem is gonna be mass moment of inertia. That's gonna happen for this first problem, where we are gonna calculate the mass moment of inertia of this given geometry. But for the next two problems, if I can get there we go. We're gonna apply the planar, so two-dimensional equations of motion. There we go. Alright, let's start with this first problem. Actually, I just went way too far. So this is gonna be, see if I can get there. So planar equation of motions are gonna be the last two problems. Okay, getting there. There we go. Cool. Alright, so let's start with this first problem. Like I said, mass moment of inertia type of problem. For this given problem, we need to determine the mass moment of inertia of the thin plate about an axis perpendicular to the page and passing through point O. So here we have the point O given in the problem. That tiny point right there, or it's attached to that type of pin, and we are given the mass per unit area, which is very important. So the way that we are gonna solve these problems, where we are given a geometry that is clearly composed by different simple geometries, we're gonna use superposition, right? So we know that for us it's easy to calculate the mass moment of inertia of a thin plate with the given radius of 0.2 meters. So we can calculate that mass moment of inertia. In fact, I'm gonna call it mass moment of inertia of the plate respect point G, where G is gonna be the center of mass or center of gravity, the same center of the body on the earth. Okay, so this is gonna be again my mass moment of inertia of this thin plate for an axis through the point G, and if we take that mass moment of inertia and we subtract this other geometry here given in the problem, this one right here, so if we do that, we're gonna get something that is close to the final answer but not quite. So let's see, go away. Alright, so this square with sides of 0.2 meters, okay, that's gonna be the mass moment of inertia of this shape respect the center of mass, which is G as well. Alright, so we're gonna get that right there. But one more thing that I'm gonna do, and it's gonna be necessary for the problem, I'm just gonna calculate the mass. I'm going to calculate the mass of the two elements. Alright, so actually I'm just gonna do it here. Mass of the thin plate. The mass of the thin plate is gonna be so the surface, which is pi times 0.2 squared, that's the surface, and then we are given the mass per unit area, which is, sorry, let's go ahead and do here the entire thing. Okay, so we're gonna have that's gonna be meters square, and then times 20 kilograms per meters square. So meter square and meter square is gonna cancel out, and from here we're gonna have that for the thin plate it's gonna be 0.8 pi kilograms. That's easy, right? Just some geometry. If you do the same for the square, we're just gonna have that basically 0.2 square, which is the area of that square, times, well, actually I don't want to forget my units here, so it's gonna be meter, okay, square, times 20 kilograms per meter square. That's gonna be equal to 0.8 kilograms. Right, so we get those two masses, and those are gonna be pretty important for us to solve the problem. So what we're gonna do next, just gonna go ahead and I'm going to say, okay, so let me see. So the mass moment of inertia of this given geometry respect point G is gonna be equal to the mass moment of inertia of the plate respect G minus the mass moment of inertia of the square respect G. However, what we need to find in this problem is gonna be the mass moment of inertia of the given geometry respect point O. And to move from G to O, we need to use the parallel axis theorem. So what we're gonna do, we're gonna go ahead and we're gonna write, okay, the mass moment of inertia of this given geometry respect O is gonna be equal to the mass moment of inertia of the plate G plus, and that's gonna be, this part right here is gonna be the parallel axis theorem, where we have the mass, okay, so it's gonna be the mass of the plate times the distance from G to O square. Alright, and then we need to subtract the mass moment of inertia of the square at G plus the mass of the square times G O, a distance square. So this right here and this right here, it's gonna be mass moment of inertia of the plate at O minus the mass moment of inertia of the square respect to O. So that's definitely what we are trying to find. Alright, so what I'm gonna do here, I'm just gonna make a snake right here. This snake is gonna go all the way here, and we're gonna solve for that equation, okay? So, alright, the mass moment of inertia, the first term for the plate, is gonna be equal to 1/2 times the mass kilograms, that's calculated right there, multiplied by the radius square. Totally entire, just trying to be consistent with my units. And at this point you can tell that the mass moment of inertia unit is kilogram times meter square, right? Okay, so that's the first term, and now we need to add the mass of the thin plate times the distance GO square. There we go. So this is gonna be just the first term. Now we need to subtract what is gonna be the mass moment of inertia of the square times the mass. Yeah, so it's gonna be 1 over 12 times the mass times 0.2 square plus 0.2 square, those are the sides, plus the distance. Okay, 0.2 meter square. If we solve for this, we're gonna obtain what is the asking mass moment of inertia of the given geometry at point O, and that's gonna be 0.133. Total is gonna be 0.113 kilogram meter square. Alright, so the problem is kinda long, but there is any major complexity on this problem. Like, it's not very complex, or like very difficult. There is a lot of steps that we need to take, but more than that, once we get to the point that we identified the simple geometries and we use we subtract or we add the moments of inertia of a simple geometry respect to another simple geometry, we can get easily to any mass moment of inertia that we need to find. Alright, so that was for mass moment of inertia. And next we're gonna start with planar equations of motion. We have already seen that. This is not really new. There are a few things that we're gonna see. They're gonna be new, but I think we'll get there pretty easily. Okay, so the mountain bike has a mass of 40 kilograms with the center of mass at point G. So right here, point G. Sorry, I'm gonna take a different color. This one. Right here, point G. Mass of gravity, center of mass of the bike, and the rider has a mass of 60 kilograms with the center of mass at point G2. So here G2, different point of mass. Okay, determine the maximum deceleration when the brake is applied to the front wheel without causing the rear wheel B to leave the road. Assume that the front wheel does not slip. Neglect the mass of all the wheels. Alright. So what I'm gonna do for this problem, the first thing that I'm gonna do is gonna be my free body diagram. Like we have done before, this is gonna be equal to the kinetic diagram. Okay, so here I'm gonna have a bike, right? So I'll try to decently draw a bike. Okay, something like that, and then we're gonna have this guy on top of the bike. Alright, not too bad. Shoes, pedals, the seat right there, and the cool hairstyle. Alright, so actually I'm just gonna hopefully let me copy it. Okay, copy and wow. And I'm trying to paste right here. There we go. Okay, not too bad. Okay, there we go. All right. So we're gonna go ahead and on my free body diagram, I'm gonna draw the forces that are applied by gravity, right? So my point G right here on this guy is gonna be the mass. So this force is gonna be the mass of the guy, which is 60 kilograms times 9.81 newtons. That's gonna be the force weight of that guy produced by the gravity. But we are also going to have another weight, which is the weight of the bike, which is 40 kilograms times 9.81, and that's gonna be newtons. All right. So we need to take into account the, let me see. Let me see. Okay. So we're gonna have two reaction forces. One on the wheel, the front wheel, which is NA, and this is given by the problem with this distance. Okay, we need to keep that in mind because we will need to calculate moments. But I'm just gonna draw the forces in here. And then we're gonna have another normal force B. But this normal force B is gonna be equal to 0 since the rear wheel B is required to just leave the road. So there is no actual forces applied by the wheel. That's what that assumption means. Then NB equal to 0 newtons. Okay. That being said, I think those are all the forces that we need to apply there. Okay. Then if we go to the kinetic diagram, we are gonna have here in this diagram we have mass times acceleration. And for this problem, the two masses that we have is gonna be the mass of the guy right there. So the acceleration of the guy riding this bike times 60. That's mass times acceleration. And then we're gonna have also the acceleration of the bike, which is gonna be the same, but now we need to multiply by the mass of the bike, which is gonna be 8 times 40. Okay, and those are also newtons, right? So if we go ahead and we apply the equation of motion for the moment around point A right here, so let's do that. That's gonna be equal to the kinetic moments that happens around point A right there, okay? So let me write that, which is pretty much, and you will see that pretty much the alpha times the mass moment of inertia, but we're just gonna solve with this, okay? Alright, so what we do, we calculate the moment that these forces produce with respect to point A. So the moment that is produced by the normal force A is equal to 0 because that's not producing any moment. Then we're gonna have a negative moment produced by the weight of the bike times this distance right here, and we can take that from the given image in the problem, which is 0.4, and the units are gonna be Newton meter. And then we are gonna have another moment that it's gonna be also minus. It's gonna be 60 times 9.81 times, and now it's gonna be all of this distance, right? All of that distance right there, and that's gonna be 0.6 if I'm correct, Newton times meter. Those are the only forces that are producing moment in the problem, and that's gonna be equal to the kinetic moments that this magnitude and this magnitude is producing at point A. So again, both of them are gonna be negative if we use the right hand rule, right hand side rule. That's gonna be minus 40, which is kilograms, times distance, which is 0.4 meters, times acceleration. And that acceleration is going to be the acceleration of the of this guy riding the bike, and it's supposed to be negative because he's decelerating. Well, we'll see. Okay, then okay, let's see. Then we also need to add the kinematic moment produced by this other term, which is 60 kilograms times, and now this distance, like all this distance, right? Well, that's kinda, there we go. That distance is gonna be 1.25 meters here, given by the problem. So 1.25 meter times A. Alright, so we need to solve for A now. Actually, all these terms are gonna turn out to be positive, so we're gonna get a acceleration of 5.606 meters per second square. Alright, and it's positive, but since we assume the acceleration to go opposite to the motion of the bicyclist, then it's pretty much this acceleration because it's going in that direction against the motion. Alright. First problem of planar equations of motion is done, And now we're gonna proceed, we're gonna do the second problem. So for this problem we have a F1 car, and I don't remember pretty well what we need to calculate, but let's read the problem. Alright, so at the start of a race, the rear driver wheels B of the 1,550 pounds car slip on the track. Determine the car's acceleration and the normal reaction the track exerts on the front pair of wheels A and the rear pair of wheels B. The coefficient of kinetic friction is μk equal 0.7 and the max mass center of the car is at G. The front wheels are free to roll, so no inertia of the wheels. That's a thing that we will study next time. And neglect the mass of all of the wheels. Okay. Alright, so here once again we're gonna write the equations of motion. To do that, we're gonna just go ahead and we're gonna do a free body diagram. We're just gonna do the free body diagram on this picture. So weight 1550 pounds, and we also know that we're gonna have two normals here, NA and NB. We need to calculate that, and then we also gonna have a friction coefficient force at this wheel right here, and that's gonna be friction at B, or force at B, equal 0.7 times NB. Alright, so we're gonna assume Y is positive in that direction, X is positive in that direction, and the acceleration is also positive, going like that. Okay. I think we're gonna use, yeah, X is positive in that direction as the acceleration, okay? Alright, so we're gonna do summatory of forces in the X equal to mass times acceleration at the center of mass. We're gonna do summatory of forces, the Y equal mass times acceleration in the Y. Then we're gonna do summatory of moments equal respect point G, so the center of mass, equal to 0. Okay, and now we're just gonna go ahead and we're gonna solve for the problem. Alright. Okay. So for the first term, we're gonna have this force right here, the traction force, which is 0.7 times NB, equal to the mass, which is 1550, but we need to divide that by the gravity times acceleration. So I believe the acceleration is one of the things that we need to calculate. So determine the car's acceleration, normal reaction on the front pair of wheels A and rear pair of wheels B. Alright, so we got our first equation right here. Second equation, we're gonna have NB plus NA minus 1550 equal to 0. Second equation right there. And then we're just gonna go ahead and solve for the last term, which is gonna be the sum of moments, which is MB right here. That's gonna be positive. It's gonna be multiplied by 4.75 minus NA multiplied by 6. All right. Also, we need to add the moment produced by the traction force, and that's gonna be minus 0.7 times NB, correct, times this distance right here, that is 0.75 feet. That's equal to 0. And you might be wondering why now we have a 0 right here, right? Like this term. So basically, there isn't any kinetic moment since the acceleration respect the center of gravity of the F1 car is going along the x direction. So that acceleration right there is not causing any inertia to this car to rotate respect point G. So there is not a kinetic moment respect that point. Okay, now we got three equations and we get three unknowns: NB, NA, and acceleration. We're gonna go ahead, we're gonna solve for this, and we'll be pretty much done with the problem. So we go ahead, we solve for this system of equations, and we're gonna have that NA, NB, and A is equal. So NA is gonna be 640 pounds force, NB is gonna be 900, approximately 910 pounds. Finally, the acceleration is going to be 13.2 feet per second square. Right, I think with that we're done for today, and I will assign you a problem to do, and also email me if you have any question.